Hey guys, and welcome back. Haven't done a video in a minute. This was a user requested video brought to you by Dramamine because I'm holding my phone while I record this video on the whiteboard. It was all I had handy. And so the video I was requested had a bunch of details, but this is the generalities. Is that a word? I'm not even sure of how you work this problem. You've got a cylinder of radius r, and of course it usually gives you a mass M, and it's got a rope or something attached, and it's going to be allowed to fall through some height, we'll say h, and to some new position down below. And this is generally the question, as you see, and what it's going to do is as it falls, it's going to rotate about this axis in the center of it. And essentially what we do when we work any problem like this, now I've got a whole series of videos on objects similar to this, just not this one. We kind of imagine that there is a beam through the middle of this cylinder. In the middle, we look at this beam and we say that this is where, directed right in the middle of the beam, this is where we have an MG. And then we go over to where this rope is attached. And at this point, a little bit crooked, but where the rope is attached, this is what we call a tension. And let me get a little better view of the entire thing. And so essentially, as you start this problem, what you need to do is take a look, and you need to do a sum of the forces X. And in this case, that's easy. It's 0. And then you need to do a sum of the forces Y. And I'm just going, for the sake of making this easy, I'm going to make going down my positive direction. So I'm going to say that we've got an mg, we've got some weight speeding this object up, and we've got a tension working against it, and then all that's going to be equal to ma. Now that's all our formulas for translational motion. But now we've got to go back and look and say, well, wait a minute, we've got a torque problem on this as well, and we've got some rotation in here. So the torque, and so essentially what you always do is you say sum of the torques is equal to I times alpha. And a lot of times problems will give you I, but anyway, in this case, we look at the torques. Well, you've only got two forces, so you could only have two possible torques, but here's the thing. You have to choose one of these two spots to be your axis of rotation. I mean, we could actually even solve this problem by picking that spot. That wouldn't be very intuitive since we know that it's rotating. We'll assume it's not slipping at that point of T. So the center of this is my axis of rotation. So the mg provides no torque since it has a radius of 0. And so we've got this tension at some point R, and we'll go back over here now for our torques. We'll say that we have a tension at some point R, and that's equal to, now if the problem gives you an I, you can substitute in your I. Most of the time this problem is going to read something like this. It's going to actually have you solve for this. So I'm going to do it AP style. And so you've got 1/2, this would be mr square alpha. And here's what's funny, guys. Essentially, I think we could say the physics in this problem is over at this point, but we can kind of continue to solve it if we need to. So here's what I'm going to do. Usually what we do whenever we're solving these problems is our two common factors. We've got this tension and we've got an angular acceleration, but I also know that linear acceleration, or even the acceleration of the center of mass of this object in this case, it's going to be equal to r times alpha. So I can use this to substitute in. So let's do this. I'm going to go ahead and have a little fun here. TR equals 1/2 mr square, and in place of alpha, I'm going to write I'm going to write big R. And then this is what's neat. R cancel square, R. I'm an angry pirate today. So all that cancels out, and I'm left with tension is equal to 1/2 MA. And guys, this is fascinating. So now if I want to solve this problem, I'm going to take this tension And I'm going to bring it back up and I'm going to substitute in there. And let's see if we can't find the little place here with a little room to write. And so I'm going to take that equation, mg minus t, and I'm going to substitute the other one in. So I'm going to have mg minus, and in place of t, I'm going to use this 1/2 ma. So minus 1/2 ma, and that's all equal to ma. And then look, the m's all cancel out. And so I've got g minus 1/2 a equals a. So I'm going to add that to both sides. And wow, this is kind of neat. So this means that g is equal to, if we bring that over, 3/2 a. Or most books are going to ask you to solve for the acceleration. So that acceleration is equal to 2/3 of g. And now that would be also our acceleration for our center of mass as well. And then we could take that acceleration if you wanted to as well. We could also find t, because we know that t is over here. So we know that t would be equal to 1/2 m times 2/3 g, which means my tension would be equal to, well, this is kind of neat, 1/3. It'd actually be equal to 1/3 mg, so that would be equal to 1/3 of the weight of this thing. So that's kind of neat. Sometimes they will then ask you to solve for like how fast it's going when it gets to that point h. Guys, there's a variety of ways we could do it. One of the easiest would be just to say v squared is equal to vo squared plus 2ah. And I'm going to say that my h initial up here, we'll just, well, here's what's kind of funny about this. It's really irrelevant here. We'll just call that 0. I know I'm going down, but this isn't a free fall question, so I'm just going to call it 1. The reason why I did it that way is my acceleration came out to a positive acceleration. So I'm going to make my frame of reference, I'm going to say this is positive in my frame of reference if we're being nitpicky about somatics. So VO square is 0. So I know that V square is equal to 2 times A, and A was 2/3 G times H, which means the square root of 4/3 GH, and that would be my velocity. This problem could also ask you to solve for this using conservation of energy. And so we'd say when it's at the top, it has a potential energy. And so we would say it's got an mgh, sorry for the terrible camera work on this, at the top. And then it has a 1/2 I omega square, kinetic energy rotational. And it has a 1/2 mv square, kinetic energy translational. And then this is what would be kind of neat. You'd have mgh equals 1/2 times 1/2 mr square times omega, which omega is v over r, plus, so again, sorry, terrible camera work, 1/2 mv square. What's really neat about this is all of the m's cancel out of this thing. And if you actually pay attention to what's going to happen, all these r's, because that's r and ultimately that's an r square, so the pirate's still at large and in charge. And we actually end up here with, if you look, this is 1/4 v square plus 1/2 v square equals, wow, gh. And by the time you do this, I don't know if you look, but that expression solves back into the same expression we already got from kinematics. But anyway, guys, I hope this helps you out with this problem and makes your life a little bit easier. Bye.